Hey again, guys. Welcome back to another second of our videos in the topic of acid-base and acid-base equilibrium. Let's pick up where we ended off. We'll look at a few structures of acids, what might make a strong acid, or a strong base and a weak base, and see where it goes from there. Here's where we ended. You should know the strong acids. These are the strong acids. One reason why is because there are so many other hundreds of weak acids that we might like to know what's a strong and what's a weak acid for one reason or another. Maybe not obvious right now. And again, the strong base is the hydroxides, sodium hydroxide, lithium hydroxide. Most hydroxides don't dissolve in the water, but the strong bases do dissolve really well and come apart 100%. So if I had 100 of these NaOH units, then 100 of them would come apart into the hydroxide and the sodium ion. And once again, know the strong acids. Go down a little bit further. The structure of HCl. The H comes apart from the Cl when dissolved in water. The water pulls that hydrogen off of the chloride, leaving behind the chlorine atom, leaving the chloride ion, and the hydrogen ion. Of course, that's H3O plus, or surrounded by many waters, but still. Here's another strong acid, sulfuric acid. The structure looks like this. Its formula is H2SO4. And the hydrogens are here and here, 4 oxygens around the sulfur. We call it a diprotic acid because it has 2 hydrogens, 1, 2, H2SO4. But interestingly, only the first hydrogen is really strong. By that it means it dissociates completely. So this is a simplification. If I say that those H2, both H's come apart from the sulfate straight away in one step, not so much. The truth is that one of the hydrogens comes off totally, and that second hydrogen is somewhat of a weak acid hydrogen. We can look at the constants if you want. Here are the equations for H2SO4. The first one coming off, millions and millions. This is 100% basically coming apart to the right. But if I look at the second hydrogen, only a small amount. So this divided by this, this one, molar concentration times this molar concentration divided by this molar concentration in a solution of hydrogen sulfate or bisulfate would be the ratio 0.012. Interesting. The more of these you see, the more you get comfortable with them. Here's nitric acid. Excuse me, nitric acid. HNO3, again a strong acid. Here's the acidic hydrogen, and it comes off easily, or this hydrogen is transferred to a water molecule easily in the presence of water. And the nitrate NO3 is left behind, floats around in the water. Here's another strong acid. It's called perchloric acid, HClO4. You know, one thing that makes a strong acid is the ability of the hydrogen to be transferred to the water. And the ability of that to happen depends on how stable this counter ion, this negative ion here, this ClO4 minus ion, how stable it is in aqueous solution, or how stable it is, period. So if this H leaves and goes over onto the water, it leaves behind its extra electron. So this whole unit, ClO4 minus, has one extra electron. How well is this conglomeration of ClO4, how well is it able to stabilize that extra negative charge? And the answer is pretty well in this case. That's what makes it such a strong acid. This can leave because it can leave behind a negative that's easily shared or stabilized or resonanced among the remaining whatever. Here's a weak acid. And this is not obvious right now, but I'm telling you that this looks like sulfate in a way. I had sulfur here and 4 oxygens around, but now I'm changing it to phosphorus. There's a central phosphorus, and 3 hydrogens surround it. 1, 2, 3. This is a weak acid. This hydrogen could come off, this hydrogen could come off, this hydrogen could come off, but by the time the first hydrogen comes off at a constant, with a constant in the area of 0.001-ish, so that doesn't happen very much. By the time one of them would come off, the time the second one will come off, or the probability or likelihood that this other one will come off, pretty small. That constant gets even smaller and smaller. So if I were to take off 1 or 2, or even speak of the likelihood of the third hydrogen coming off. By the time the third one leaves, I guess this group that's left behind is not able to stabilize the negativity quite as well as say sulfate or perchlorate or something like that. The constant gets smaller. This is always the case for any polyprotic acid where I have more than one proton that can come off. The first proton comes off easily, the second one not so easily, the third one a lot easier. And so if I just had phosphoric acid in the water, there'd be mostly this. Actually, mostly this. A little bit of this, a little bit of this. A teeny weeny of this. And an even teenier, eenier, weenier amount of that. Food for thought. Here's some other polyprotic acids and their constants. Arsenic acid, carbonic acid, sulfuric, yeah, the first one is large for that one. Anyway, this is a weak acid, even weaker and even weaker by the time I removed all three of those. What else do I have? Ascorbic acid, vitamin C. The first hydrogen comes off to the tune of this constant, and the second hydrogen comes off to the tune of the 10 to the negative 12 constant, which is a lot smaller. Interesting. Another weak acid, nitrous acid, HNO2. The only reason I know it's a weak acid is it's not in my memorized list of strong acids. Nitric acid is strong, but nitric has that extra oxygen on this central nitrogen. But now that I know it's weak, I start to draw equilibrium arrows, right? I also have that in my phosphoric acid up a little bit higher. But nitrous acid, equilibrium arrows. The constant here looks like 0.0004. So the ratio of this times this to this molar concentration, pretty small. Although I've seen a lot smaller. Yeah, I could call it a strong weak acid if that makes any sense. One of the stronger weak acids. Hypochlorous acid, a pretty weak acid. Got a chlorine, got an oxygen, got an acidic hydrogen. The equation looks like this. I drew equilibrium arrows because I'm not a strong acid. I write a constant expression, H plus and OCl minus, multiplication upstairs. There's my original concentrate, not the original species, how much of it I have left over. That's very small. 3.5 times 10 to the negative 8, I think, if I counted those zeros right. Here's vinegar. Vinegar is the most famous, most common weak acid in the world. Let's see. Hydrogen. Lastly, this hydrogen. This is the hydrogen that can come off. This is the one that dissociates. And there are many ways to write the formula for vinegar, but one of those H's that it's attached to one of those oxygens, that's the acidic hydrogen. And those hydrogens attached to the carbon, they don't come off. I mean, they could possibly, but in most reasonable situations, never. Here's benzoic acid. Benzoic has a benzene ring here with some resonance of double single bonding, and the carboxylic acid group, carbon double bond O, and then another oxygen here, and there's the hydrogen hanging off of that. Yeah, it's pretty weak acid. It's actually a little teeny bit stronger than vinegar. Here's vinegar, 1.8 to negative 5. Benzoic acid, 6.4 to negative 5. So you know what? This little thing that's hanging off the carboxylic acid group, that has something to do with how strong the acid is. In organic chemistry, you'll study that quite a bit. I don't know how much time we'll have to go into it in our studies this chapter. Another view of acetic acid. The carboxylic acid group over here, C double bond O, OH, and whatever else hangs off over here makes it a stronger or weaker acid. Other examples, citric acid, malonic acid, oranges, limes, lemons, grapes. Let me zoom in on this little thing. Let's get some cartoons going for what's a strong acid and what's a weak acid. Here's a strong acid, the HA or whatever HA is the generic term for the part that's attached to the acidic hydrogen. But if they come apart totally, it's a strong acid. But in this one, the HB, I don't like the term. I don't like the way you use the B here, but they did. So there you go. In this one, this is a weak acid because looking over here, after equilibrium has been established, only one unit out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only 1 out of 10. So maybe the percent dissociation on this acid is only 10%. So out of 100 of these, only 10 of them come apart into the ions. And indeed, that's the way we decide what's a strong acid and what's a weak acid. So, which category would these acids fall into? Or I mean to say maybe which beaker represents each acid? HCl, memorize it, strong acid. Looks like this. HOCl, weak acid. Don't have to memorize it because it's a weak acid, but you know that it's not on your list of strong acids. HNO3 is nitric acid, a strong acid. HNO2 is nitrous acid, a weak acid. Looks like this. Not very many of them come apart. Hydriodic, strong acid. And I forgot what that is. Maybe it's citric acid. Or ascorbic. I think it's citric. A weak acid, they go over here. So, anyway, think about the cartoons. Another way to say it is the water able to pull the bond apart between the acidic hydrogen and whatever else is left over? Well, with a strong acid, the answer is yes, because there's a weak attraction between the H plus and the A minus, and water just yoinks that hydrogen ion right off. But with weak acids, not so much. Weak acids are weak because the bond between the acidic hydrogen and whatever else is bonded to is strong, and so water cannot break that bond. Here's another interesting trend. As I go down the table, hydrofluoric, hydrochloric, hydrobron. Oh, this is an example of what I was speaking of right here. Sorry to turn the pages so quickly. So this is a fairly strong bond. Look at that. And water's not strong enough to break the HF. Technically, HF is a weak acid, but it's a fairly strong, one of the stronger weak acids. But still, that bond is stronger than those. If you think back to your ideas on bonding and molecules, you could probably explain that. Oops. All right. What about the strong bases? You should know your strong bases. Lithium, potassium, sodium, rubidium, cesium hydroxide, also strong bases. Calcium hydroxide, strong base. Doesn't dissolve really well in water, but pretty well. Some uses for strong bases. They're all around us. Actually, my bad. Ammonia is a weak base, and the carbonate's a weak base. I don't see any OH in that. I don't see any OH in that. So this thing and this thing must be interacting with the water to create a little bit of hydroxide in the water. So a strong acid, again, comes apart totally in water. None of it stays together. The chloride's surrounded by water. The sodium ion's surrounded by water. No. Oh, that's hydrochloric. My bad. The hydrogen, the acidic hydrogen, the protons attracted to the water. But a weak acid does not come apart totally in water, just a little bit in water. Strong bases dissociate totally in water. If I had solid sodium hydroxide, many strong bases are solids. I dissolve them in water. They break apart totally into aqueous solution. Of course, this would be surrounded by water, and this would be surrounded by water as well. The water orients itself, positive side, negative side, to be attracted to the oppositely charged ion. But weak bases like ammonia, often weak bases will interact with the water itself, pulling it apart into hydroxide. That's where the OH comes from with the weak bases. We'll talk more about that in a future video. Alright, but what about this deal? A strong acid will have a weak conjugate base, and a weak acid will have a strong conjugate base. Strong acid, very weak conjugate base. Strong acid, very weak conjugate base. Strong acid, very weak conjugate base. I am not afraid of these ions. They're pretty much harmless, but I am afraid of these acids. Conversely, I'm not too afraid of these as acids, but I might be afraid of their conjugate bases. If you have a weak acid, you have a very strong conjugate base. So it seems to go backwards, but if you think about it, it makes a little bit of sense. In terms of, if I have a strong acid wanting to give up its hydrogen, then it will and become something more stable. Or if I have a weak base, a weak acid will want to, if I had a conjugate base that wanted to become a weak acid, then it would gain a hydrogen from something and somewhere and somehow. Are there trends? Let's see, as I go down the family, it gets less acidic. Oops, decreasing bond strength, my bad, increasing acidity. And as I go to the right, I also get more. So this is a stronger acid than this, and this is a stronger acid than this. I gotta stop, guys. You've been listening for too long. Thanks, I'll catch you again soon.